My name is AKM Amanatullah. I'm a PhD candidate at UBC Okanagan campus. My co-authors are Dr. David Armstrong from University of Klagenfurt and Dr. Khaled Hassan from UBC. 360-degree content is becoming increasingly popular. It is now commonly used for immersive experience in scenarios such as gaming and training simulations. Large curve displays offer an ideal platform for viewing 360-degree content, and their shape naturally wraps around the user and matches the panoramic view of the 360 content. However, these displays typically limit the user's view to 180 degree. This means the half of the content is hidden off screen, and we need a way to bring off-screen content to on-screen. Users naturally turn their head towards a region when looking or interacting with it. This makes head movement a promising option to bring off-screen content into view. However, we need to know how we can effectively use head movement to bring off-screen content into our view. Researchers have showed that mapping functions that translate physical movement into workspace movement are helpful for navigating large information space. In this work, we explored how leveraging head movement with mapping functions for navigating off-screen content on wall-sized displays. More specifically, we conducted 2 user studies to achieve the goal. In our first user study, we explore a set of mapping functions where head movement can be mapped to workspace movement. And in the second study, we compared the best performing head-based methods against industry standards, which are controller-based techniques. Now let us start with study 1. To understand how this works, let us look at a quick demo of the video of our study 1 task. Here you notice that the participant uses the head movement to find the blue target and brings it directly into the center of the screen to finish the task. We explored 3 rate control mapping functions: linear, sigmoid, and polynomial. And you'll find the details of these in the paper. From a very high level, based on the mapping function, the speed of the workspace increases the farther you turn your head. Each function has its unique characteristics. For example, the polynomial mapping function results in very slow workspace movement for small head rotations, but a rapid increase in speed for larger head rotations. We also explored 4 zone control functions. These are inspired by flick-based scrolling on smartphones. The user had to perform flicks with their head to move the workspace. As we saw in the demo earlier, the task was to bring an off-screen target to the center of the screen using head movement. Once done, the user confirms the selection by holding the controller joystick. We choose 3 different window sizes, that is 400 centimeter, 600 centimeter, and 800 centimeter. We also use 3 target distances, that is 500 centimeter, 750 centimeter, and 1000 centimeter from the center of the screen. These are placed along the curved surface and are off-screen. To summarize, we ran a within-subject study where we evaluated 7 mapping functions with 3 display windows and 3 target distances. We had 28 participants. Due to time constraints, we are summarizing the results. From the study results, we found that the polynomial function was the fastest. Also, rate control mapping function were significantly faster than the zone control functions. We also found that the polynomial was more preferable in terms of the NASA-TLX criteria. So the polynomial was the fastest mapping function with the least workload. However, we need to see how it compares against commonly used industry standard techniques. For our second study, we moved from an abstract task to a realistic map navigation task. We wanted to see how our best performing head-based polynomial technique actually compares against standard techniques. In this study, we consider a map navigation task where participants had to access 4 country markers that contain their corresponding population information. Let me first show you the task on a 2D map, and then I will show you the actual 360 demo. So the participant had to select the markers in a certain order to open the pop-up information, which contains the population information for all 4 countries, and they had to add them to a list. So here are the 4 markers. And this is the exact same layout as seen in the 2D demo, but wrapped onto our 360 workspace. To avoid learning effect, we prepared 6 sets and we divide them into 2 country clusters based on their angular separation. Here you can see the video with our task. So on the left, you see the black panel that shows which country to select next, and the participant had to navigate the map and select information from all 4 countries in the given order. We had 3 navigation techniques. With head polynomial, the user navigated using only their head movement, just as you've seen in our study 1. With drag and flick, users held a controller button and moved their hand to drag the map. With the push and release, the user simply pushed the controller joystick left or right to move the map continuously. We had 3 navigation techniques and 2 country clusters. We had a total of 18 participants for our study 2. From the results, we observed that the head polynomial technique was faster than both push and release, and also the drag and flick methods. Also, the head polynomial took the least effort, while the drag and flick required the most effort. Moreover, we found that 12 out of 18 participants ranked the head polynomial as their most preferred technique. Here we summarize the results of our study 2. We found that head polynomial technique was the fastest technique, drag and flick caused the most effort, and the head-based navigation was most preferred. Based on the results of the 2 studies, we now provide the following recommendations. We suggest designers to consider the polynomial mapping function for head-based navigation. Also, the designer could avoid clutch-heavy drag movement on the large displays, as it takes more time to navigate the workspace. And they could also offer the push and release as a secondary option to the polynomial function. But for future work, we would like to test on displays with different curvatures. We can also extend our one-dimensional navigation task to 2 and 3 dimensions. And finally, exploring multi-user navigation would be an interesting future direction. Thank you for listening to our presentation. I would like to add that I'm graduating this month, and I would like to start any postdoc position if available. So if you have any postdoc opportunities, feel free to talk to me after the session.